The speaker is Dr. Chao Chen from Hong Kong, UST. Okay, you can start.
Yes, thank you. Thank you for having me. I'm very happy to be here to share share our recent work on induced gravitational wave from statistically anisotropic scalar perturbations. This work is finished with Dr. Azwesa Ota. Okay, so here is my outline. And at first, I will introduce the anisotropic stochastic gravitational background briefly, and then move to the induced gravitational wave, which originated from this stochastically anisotropic scalar perturbation. And finally, I will summarize my talk. As Professor P has already given a very comprehensive introduction to promoted by Ho and the induced gravitational wave, so I will go through the relevant part very quickly. So yeah, and okay, so usually we always assume our background is homogeneous and anisotropic, but we still have the possibility of producing anisotropic stochastic gravitational background. The origins can be classified into two classes. One is the initial condition. If you have a non-Gaussianity, let's say this non-Gaussianity can modulate the short and the long wavelength. So you will have the anisotropy. And another possibility is the anisotropy background, and so on. You have any other non-trivial initial condition. And another possibility is from the propagation effects. I mean, just like Sandy photon, we also have the similar SW effects for graviton. Okay, graviton propagates through the perturbed universe where we experience the redshift, so it will produce anisotropy in their energy spectrum. So okay, so the anisotropy SGWB, we can also test the production mechanism for the primordial gravitational waves. And recently, there is a paper from Lisa group. They have discussed the probability for Lisa to detect this anisotropy in stochastic gravitational background. Okay, so and hopefully in one day we may detect the all sky map for gravitational wave, just like for SMB photon. Okay, let's say how to describe the anisotropy for SGWB. So we usually use the energy spectrum, which is defined in this way. Okay, so usually for the isotropic gravitational wave, we always integrate out this angular part. So, but here we have anisotropies. We have a preferred direction, so we have to remain this angular integral. And similar to the SMB treatments, we can also define the angular spectrum for SGWB. Okay, these components are the components in terms of the spherical harmonics, just like SMB photons. Okay, and until now, in many studies on anisotropy SGWB, people always consider or assume the 1-point correlator of the omega GW energy spectrum is 0. But in our study, we will find that even the leading order, even at the 1-point correlator, because of the anisotropy source, you will produce anisotropy for the 1-point correlator. Okay, so okay, let's take a quick look at the p-batch formation model. Okay, so if you have over the density region at the earlier universe. When this region cross the Hubble horizon at the radiation domination, and if the density contract is larger than the delta C is the threshold, and this region can start collapse and collapse into a black hole. That is the roughly the physical picture for PPH formation. Okay, so and we can use the classical genes theory to estimate the threshold value and the PPH formation mass. Okay, this we usually we can simply use the horizon mass approximation. That is the mass of PPH formed is roughly equal to the horizon mass. Okay, so you can relate the PPH mass to the formation time, and in this green box we can see that at various times you can produce various very wide range PPH masses. So this is I think this is a key feature different from the astrophysical black hole. So okay, so just because this wide mass range, PPH can relate it to various cosmological and astrophysical phenomena. And for example, the most important that when the mass is larger than 10 to 15 grams, it can survive to present. So and its behavior just like a cold dark matter, so it can be the cold dark matter candidate. And another motivation is PPH can explain like a Virgo detective events, and PPH can also be the seeds for supermassive black hole in many galaxies. And for the very large black holes, their Hawking radiation is very significant. So the Hawking related particles can influence some early physical processes like Big Bang nucleosynthesis and SMB, and it can also explain the extragalactic background and gamma ray bursts and so on. And inversely, you can use the observational of this phenomena and to put the constraints on PPH balances. So as you can see in the future, there is a summary of the various constraints on PPH balance during various mass range of PPHs. So in this sense, we can use PPH to detect the early universe, even though we haven't detected them. Okay, so okay, here okay, Professor Pia has already introduced this part, the cross correlation between the chromatic black hole and the induced gravitational wave. Okay, so for a very large chromatic density perturbation, on one hand, we have the PPH formation events, and we can estimate their abundances in this way. And on the other hand, due to the second order cosmological perturbation, we have the secondary component between the scalar perturbation and the second order tensor modes. So you can, this large enhanced scalar perturbation can induce gravitational waves. So, and this spectrum, energy spectrum of the induced gravitational wave is proportional to 2-point correlator and proportional to the 4-point correlator for scalar perturbation. And this is the square of the power spectrum. So you can say that once you have some primary black holes, you must have a certain amount of induced gravitational waves. So we can use this induced gravitational wave to detect the parameter black holes. And another thing is that, so the PBH formed at small scales, and until now we don't have any reliable knowledge about the small scale perturbation and the small scale physical process in the very early universe. So if we have a PBH formation, we must have the induced gravitational wave. So we can use the induced gravitational wave to detect the small scale scalar perturbations. Like, for example, the non-Gaussianity of the small scale scalar perturbation, which is not accessible through the SAMB observation. So, and in this paper by Chao Chen and Suzuki-san, they have discussed the non-Gaussianity effects on the induced gravitational waves. So, okay, let's take a look at dynamics of induced gravitational waves. And here we have the equation of motion for gravitational wave in terms of the source. And this source is the TT part, the transverse traceless part of the source. And we know that we can use the Green function method to solve this equation. And the general solution is like this, with the homogeneous solution plus the special solution, that is Green function. GK is Green function here, and satisfy this equation. And here we drop the homogeneous part. This part is just a linear gravitational wave. It's the vacuum solution, so we don't focus on it. And we can calculate two-point correlator for induced gravitational wave, and it's expressed in this form. And so if you have the source, you calculate the source correlator, you will get the induced gravitational wave spectrum. Okay, for different source, you can calculate the different signals of induced gravitational waves. So here we focus on the radiation domination epoch. So the first step is to expand the metric to up to the second order. For the first order, we only have the first order scalar perturbation, and the second order, we only consider second order tensor modes. And in Newtonian gauge, we have this form for metric perturbation, and here we ignore the anisotropy stress at the linear order. So we have the same far body potential here. And from the second order Einstein equation, and we can get the source term for induced gravitational wave. This is the bilinear, not bilinear, it's a combination of the first order scalar perturbation. And okay, now we get the source term, and we can calculate the induced gravitational wave. So, and here in our paper, we consider anisotropy scalar perturbation. This is in previous work for induced gravitational wave, people always consider anisotropy scalar perturbation. Here, as I mentioned before, just mentioned, the induced gravitational wave can respond to the small scale scalar perturbation. So if you have a statistically anisotropy scalar perturbation, it can imprint some signals in the induced gravitational wave. So okay, so and as we all know, in the anisotropic inflation, we already have the concrete model to produce this anisotropy primordial scalar perturbation. Here you just introduced a vector field. So this vector field will introduce a preference direction in power spectrum. So you will produce the anisotropy. Okay, so for anisotropy scalar power spectrum, we can parameterize in this way. Okay, so this P zeta is the isotropic part of power spectrum, and the AL is the coefficient, and the PL is the Legendre polynomials. Okay, and according to the current SMB observation at the SMB large scales, we have these constraints on E2. Okay, and in our work, for simplicity, we assume this is a constant. So, okay, and so in anisotropic inflation, we only have the monopole and the quadrupole. So here we only consider the monopole and the quadrupole of the source. And another thing is, since we here we assume the anisotropy scalar perturbation, but we still assume the homogeneous. Homogeneity is always satisfied. So you can see that the all terms of the AL will be the 0. So we do not have the dipole here. Okay, so the D is the preferred statistical direction. So when you have this direction, the SO3 rotation symmetry is broken to the SO2 symmetry. Okay, for the normal case, the isotropic universe, we have this the monopole is equal to 1, and the other terms are zeros. Okay, so follow the previous treatment, we can get the power spectrum for induced gravitational waves in terms of the multiple expansion for the source. Okay, here we can see we have the kernel function. The kernel function is from the source, and we have the power spectrum of the source, and we have the Legendre polynomial, the combination, the two Legendre polynomials, two series of them. So if we expand the source up to the quadrupole moment, we have these three types of combinations: 0, 0, 0, 2, 2, 0, and 2, 2. Okay, the 0, 0 gives you the monopole moments of induced gravitational wave, and the 0, 2, 2, 0 gives you the quadrupole moment. But for the quadrupole source, you will get the monopole and the quadrupole and the L equals to 4 poles. This is because the production of the quadrupole moments can expand in terms of monopole, quadrupole, and L equals to 4. So, and okay, so in the similar way, we can expand the omega GW in terms of the monopole and the Legendre polynomials, and omega L is the monopole here. And yes.
Dr. Chen, you have 5 minutes.
Okay, thank you. So here we have the expression here. The delta function refers to the isotropic source, and the QL function is the contribution from the isotropic of the source. So here we can see that the most interesting is that even for the monopole moment of induced gravitational wave, you have the contribution from the quadrupole of the source. So that means, in principle, you can detect the anisotropy even for the monopole moment of the induced gravitational wave. So it will be easier for detect the quadrupole moment and the higher order pole of the induced gravitational waves. Okay, so and here we can consider the concrete the source for isotropic part, and you can get the induced gravitational signals. Here we consider delta peak source here, and you can see this monopole and quadrupole and L equals to 4 pole, and anisotropic is always positive. But for monopole and quadrupole, you have the zeros for them, and these two blocks show the zeros in terms of the A2 coefficients. And another thing here is that since the power spectrum is positive, so we have this constraint on A2. But this we have to say this constraint is merely due to the truncation of the multiple expansion. If you expand to all of the multiples, you will always get the positive power spectrum. So this is for consistency, we consider this as the constraints on A2. And okay, since the zeros, we have the local minimum for multiple moments. You can see in this plot, we have the local minimum of the induced gravitational wave for the multiple. Okay, this is a distinct feature compared to the anisotropic induced gravitational waves. Okay, and also for the infrared scaling, we can find that it is same with the isotropic induced gravitational wave, because in the infrared limit, the leading order is always the multiple. So there is no direction. So that means isotropy doesn't affect the infrared scaling unless the coefficients AL depends on K. If it depends on K, it will contribute the extra K power. So it will change the infrared scaling. And another case is the log normal, which is more realistic, and it can cover the delta peak for the narrow peak, and it will approximate to the scale invariant when the broad is when the peak is very broad. Okay, and this case is firstly studied by P and Sasaki-san in their paper, and we followed their paper, and we calculate the monopole and the quadrupole and four pole here, and yeah, here is our results for the narrow peak. So for narrow peak, we can use the stationary approximation for analytical calculation. But for the broad peak, and also here is the infrared discussion. The infrared is different, as Professor B has already discussed this part, so we just pass through. For the broad peak, because our due to the anisotropy, the kernel function is very complicated, so we just refer to the numerical calculation here. As we expect, you can see that for the broader peak, the power spectrum will become the broader. Okay, so and the 0 points will move to the right hand side. Okay, when we increase the peak. Okay, so here is an open question. So until now, to our knowledge, Ph formation has not been discussed in terms of the stochastic anisotropy. So the induced gravitational will be much more interesting when the source is enhanced, because it's second order. So usually it's very small. You have to enhance the source. So in here, in anisotropy inflation, the power spectrum can be described in this form. And G2 here is somewhat a free parameter. So if we can amplify the G2, so we will amplify the power spectrum. So in principle, can produce the chromatic black hole. So yeah, this is the we leave this to the future work. Okay, here is my conclusion. In this gradual way can be detect the small scale statistics of chromatic scalar perturbation, and in our paper we consider the induced gradual way from anisotropy scalar perturbation, and we derive the monopole, quadrupole, and Lx equals to 4 pole of the induced gradual way. And perturbation formation in terms of the anisotropy will be interesting. So, okay, I will stop here and take question. Thank you very much.
Okay, thank you. Anybody has any question?
Can I ask a question?
Yeah,
Yeah.
sure.
Yeah, I noticed that you mentioned this cross correlation relation between the induced gravitational waves and primordial black holes.
Yes.
So do you have any observational characteristic things in the primordial black hole side for the anisotropy?
Yeah. But yeah, we don't have any observational part in our current paper because we just focus on the energy spectrum at the perpetual formation epoch. Yes, because besides the anisotropy from the source, you also have the anisotropy from the propagation. So we didn't consider the propagation effect. So yeah, so we just calculate. We didn't compare the our results with the observation at the present. Yes.
So you mean you didn't consider the effect of anisotropy on the primordial black hole formation? No.
Sorry.
You didn't consider the effect of anisotropy in the primordial black hole formation.
Yeah. Right. Yeah.
I see. Okay.
Yeah. Yes.
Okay. Any other question? Professor Kim?
Okay, I'd like to ask questions. If there is some initial vector field, then it means there is some specific directions. And then such a specific direction will make the CMB be polarized to some directions. And in that case, we should find some direction dependence on the CMB. So we should find two specific points on the sky. Can you find such a things?
Yes, but for yes, we have the CMB constraints on anisotropy. Yeah, I have mentioned here. So until at the present we have these constraints on A2, but this is on the large scales. We don't have any constraints on the small scales about the anisotropy. So in principle, it has this anisotropy will imprint on the CMB photons, but it's very difficult to detect the small scale anisotropy. So yes, so one way is the induced question. If you have the enhanced anisotropy, you will have the large induced gravitational wave signal, and you can know you have the primordial anisotropy. Yes.
Okay. Yeah. Okay. Thank you, and thank you for all the speakers of this session. Okay. Thank you. And okay.